So remember in the last lecture we talked about 14.5, we talked about cylindrical coordinates. And so what we're going to do, and they were kind of a generalization of the idea of polar coordinates where we kept, right, the x, y, we treated like polar coordinates and then we kept z the same. So spherical coordinates are another generalization of polar coordinates, but this time we kind of, well, we're a little more precise here. And so let me just do this again. All right, so again, assume that what I'm drawing makes sense. So we have some point here. Well, let me do this. I'm going to just fill in some values as long as we're here. So when we converted to spherical coordinates, what's this length called?
Oh.
R, and then this angle is theta, right? Okay. That angle is going to be the same thing here. Okay, we're going to use theta still. But remember, what was the idea of polar coordinates? It was, well, we're going to take an angle and then we're going to measure how far we are from the origin, right? That's what the R represented in XY. And so we're just going to do the 3D version of that. We're going to need a variable that represents how far we are from the origin. That's going to be rho. Okay? And I guess it doesn't matter. Here's your z. So here's your point. X, Y, Z. And so let's just write them all up. So in polar coordinates, how do we, in cylindrical coordinates, how would we represent that same point? What we did last time. R and theta will represent the x and y, right? So r theta, and then we leave the z alone, right? And so in spherical coordinates, what we're going to do is we're going to say, okay, rho first tells you how far you are away from the origin, right? Theta represents the same thing. It tells you how far to rotate in this direction. And then we're going to throw in a third variable. So we're here, and then we want to know where to be rotated like this. And so we're going to put in a third angle, a third variable, which we call phi, and that's the angle from the positive y or z axis, right? There's phi. Okay. All right. The theta, well, in this case, let me just say, so life doesn't get too ugly here, because again, you might theoretically let your thetas be anything you want and your phis be anything you want, and you'd have a ton of different ways to represent the same point. But we make restrictions here, so we restrict. Rho to be greater than or equal to 0, so we only will talk about positive rhos in this case. And so again, the theta can be anything. Essentially all we need is 0 to 2 pi, right, to wrap around one time. And if we allow the theta to wrap all the way around, in order to represent a point, what does phi have to range from? It doesn't need to go all the way. It can go from 0 till, we don't have to go all the way around because the theta can bring us to the backside, right? So if we wanted a point over here, we can let the theta turn us around there, and we still just need to go between 0 and pi. Does that make sense? So we also restrict the phi between 0 and pi. Okay? All right. I think I'll squeeze these up here. Identities. Again, you just apply the distance formula, and so, like always, probably the most important identity, x squared plus y squared plus z squared, that gives you your rho squared, right? It's just a 3D version of the Pythagorean theorem, basically. Right, x squared plus y squared is r squared, that's this distance. So this distance squared plus z squared equals the radius of that new triangle squared, right? You're just combining those things, and I think I'll leave off the details. Remember, x is what? R cosine of theta, right? But look at what r is. If this is r up here as well, right?
Sine.
And And so if you take R, R divided by phi, right, you have sine of your phi, right? There's your angles here. And so you have R over phi is sine, so R is phi times sine of, or sorry, rho times sine of phi. Rho times sine of phi. Does that make sense? And so I'll just write it out. So rho sine of phi, that's essentially your R, and then we know x is R times cosine of theta, right? What is y? It's R times sine of theta, right? That's R still, and so we just replace it rho sine of phi, sine of theta. So, I mean, you can just memorize them, but you know, I'd almost just remember what R is and go from there. What is z in terms of theta and rho? Okay, rho cosine. Yeah. Same argument as before, right? If this is your angle here, then z over rho is cosine, right? And so you get z is rho cosine. Okay. What else? I guess I'll squeeze these in. We use these a little less often, but just like before, tangent of theta is going to be y over x, right? Those are still representing the same thing they did. And then similar argument, you get that cosine of phi is the, I don't know why I'm putting this in this way. Well, I guess I'll do it this way. So if you know x, y, and z, you can find rho. And so if you wanted to find phi, right, if you know z, x, y, so if you know x, y, z, you can find phi using this formula. I guess that's my point. Okay, so let's do the same thing we did last time, which is first just sketch a few points so we get a feel for what these look like. And then after that, we'll sketch some objects. So plot the following points. Okay, so again, I'm listing these points in spherical coordinates. So don't worry about getting perfect pictures. You can draw them all on separate axes if you want, or you can combine them into one. Just think about what these mean, right? So the first number is our distance from the origin, and then remember what the phi, or the theta and the phi represent, and try to sketch in what these guys are. Again, the big idea here is that you're able to sketch it well enough that you understand what is being represented. That's more important than me necessarily understanding. All right, let's try to go through these. So that first one, again, the distance 2 we'll worry about at the end. What is the pi over 4 telling us?
70.
To to come 45 degrees right between x and y. So we're going to split this. I'll just draw it like that. And then the pi over 3 means to come 60 degrees, or yeah, 60 degrees down from vertical, right? So we're going to come out at, so let me just do this. Pi over 4, and then you're just going to go, right, you're going to go up to a distance where that angle is 60 degrees, or pi over 3. Does that make sense? And so you're going to end up at some point here where that is 2 units out. So if this corner, this is the x-axis, the y-axis, and the z-axis, right? We just turn 45 degrees here, and then we drop down 60 degrees there, and so we come out along that line, right? Okay. Here, I'll just squeeze the other ones in here. So what's the next one? 3 pi, so where's pi? So that's all the way back around to the negative x-axis, right? And then we come down pi over 4, so that's 45 degrees, so we're going to be out here, and we're going to go straight up until we get basically there. So 3, that's pi over 4, and that's 1. So just label it so you show what you realize where those things are. And then finally, the last one. So pi over 2 puts us where? No, 90, right? Yeah. So it puts us on the y-axis. And then 2 puts us 2 units out. And then what's 7 pi over 6? So from here, there's, oh, I just lied to you. I wanted this between pi. I screwed up here. I don't want, that's bigger than pi, right? That's not what we want. I want it just bigger than pi over 2. So let's see, pi over 2 is 3 pi over 6. I want it to just go to, yeah, that's fine. I'm going to write it as 4 pi over 6. So you can clean that up, obviously it's 2 pi over 3, right? But what angle is that then?
120?
Yeah, so it's 90 plus 30, yeah, so 120. So 30 past 90, right? That's all I cared about. And so we have this like this. We're here, right? So we're coming all the way around to here. That's pi over 2. And then we're going 30 degrees past vertical, right? And then we're dropping straight down like that. So that was 2 units away. So there's your point there. Make sense? So sitting straight under the y-axis at that angle. Okay. So I think that is good enough. Looks a little bit messy there, but hopefully you get the idea. Oh, I want to keep the identities up. So again, with these identities, eventually you memorize them, or I don't really have them memorized. I just think about what they need to be as you're doing them. But you know, it's probably worth. Okay. So maybe that's all. I think those are the only ones we need for now. So we'll come back to those in a minute. We don't need them for this first example. Sketch. Following. So we'll do a couple different ones here. Let's just start with one like this. And again, this should tell you why this coordinate system has this name. So if we just let rho equals 3, right? What does the rho represent? The distance from the origin. And so if rho is 3 and theta and phi are anything, what do we get? we're 3 units away from the origin, and we're any angle in both directions, right? So what's that give us? Yeah, a ball, a sphere, right? So this is going to give us a sphere of radius 3. Does that make sense? All right, let me give you another one here. So some of these I'm just going to describe the regions. Let's say rho, phi, or theta, such that 1 is less than or equal to rho, less than or equal to 3. 0 less than or equal to theta, less than or equal to pi, and 0 less than or equal to phi, less than or equal to pi over 2. So try to draw this region out. Again, the rho's range between 1 and 3. So again, rho equals 1 would be a sphere of radius 1. Rho equals 3 would be a sphere of radius 3. So you're in between 2 spheres, and then figure out which parts of those spheres you're interested in. Okay, so let's look at this one. So again, our distance from the origin ranges between 1 and 3. Our thetas are between 0 and pi, so where's that? Between the angle ranges from positive x-axis all the way around to that negative x-axis, right? And then how about the phi from 0 to pi over 2, so that's from vertical to horizontal, right? So your angles can be right anywhere between 0 and pi for your theta, and then your phi's between horizontal and vertical. And so hopefully, right, we go from 1 out to 3, and then we allow our arcs to be anywhere from here, right? Oops. There, something like that. So you just basically, that looks terrible on that one side. All right, so you have this circle on the outside, right? And then you have this sphere on the outside and a sphere on the inside, and you're taking everything in between those guys. So this, I'm going to leave it like that. Does that make sense? So it looks kind of like, you know, when you see pictures in like a geology book where they've taken the earth and trimmed it out and you see the core is some color, right? Think of that. That's your core inside there, and then you have this rest of it. You're just taking slices like that. And so this is the place, or one of the places where spherical coordinates will be so useful, right? Because it's really, that's a really easy region to describe. If you tried to describe that in rectangular coordinates, it would be a mess, right? This would be z equals the square root of 9 minus x squared minus y squared. The inside one would be z equals the square root of 1 minus x squared minus y squared. But they don't overlap for the whole region, right? And so you have to talk about, you know, when you're inside this circle, this is your bottom, that's your top, and then once you get outside that circle, the 0 is your bottom, right? And that's your top. It'll be a really painful region to try to describe that way. And so this is a lot easier to tackle using this method. Okay? So, I think that's decent. Convert. This one will be a little bit tricky. Let's do So this is going to be a really important function, and so I want to view it both in cylindrical and spherical. So z equals the square root of x squared plus y squared. And so maybe we can try to sketch it before we even do anything else. Right? So how did we sketch things before? We took them and we said, well, we did a bunch of different things. We had spheres, right? We just kind of knew it was the formula of a sphere and sketched it. But if we had z as a function of x and y, the first thing we did was just let one of the variables be 0, right? And so if you let's just do x be 0, what do you get? Z equals the square root of y squared, which is, it's not just y though, it's the absolute value of y, right? And so you would get the absolute value here, and then the same thing here, right? With the x's, you get absolute value, and so that's a little bit awkward to try to see. But it should be a cone shape. Does that make sense? So with solid sides. So let's just confirm this as we move along. So the conversion to cylindrical shouldn't be too bad. What do? We replace square root of x squared plus y squared. So cylindrical, we replace the x squared plus y squared with r squared. And then z is, I'm just going to say r. This actually would allow, with this statement, maybe I'll put it this way. Right, this only works if r is positive. So that gives you the top half of the cone. If you allow every r, then you allow negative, the negative part of the cone. It'll just be the negative reflection. Okay, how about to spherical? And this will be where it gets a little bit trickier. So let's go back to the original. Z equals the square root of x squared plus y squared. And maybe I'll let you chew on it for a second and see if you can come up with a nice equation. So that equation should just involve phis, thetas, and rho, right? And so we'll want to use the identities that we had just put up over there. If you don't see it right away, I'll give you one hint first. Square both sides. Anybody getting anywhere?
Just got a number.
Well, yeah, so let's look at this. So z squared could be replaced with what? Rho cosine of phi, right? So you could get rho squared, maybe I'll do it that way. You could get rho squared cosine squared of phi equals, and if you just, I'll give you another way to do it in a second, but if you just blindly plug in what they are, right, then this guy becomes, well, I'll just write it up. Rho squared sine squared of phi cosine squared of theta, right? Plus rho squared sine squared of phi sine squared of theta, right? So what's that left-hand side become? Not just one. What is it?
Rho squared sine c squared.
Yeah, rho squared, and you still have that sine squared of phi, right? The cosine squared plus sine squared of theta add up to 1 until you get that. And so now you could cancel out the rho squareds, right? And you could get this. Let me write it this way. Sine over cosine is?
Equal.
Well, sine over cosine is tangent, right?
Oh yeah.
So if I divide both sides by cosine, let me just say, we'll take the square root. So sine is cosine really plus or minus, but let's not worry about it. So you get sine equals cosine, that's the same as tangent equals 1, right? When does tangent equal 1?
Oh, pi over 4.
At pi over 4. Oh, I've got phi, not theta, sorry. Pay attention to your to your angle, right? Phi is pi over 4, does that make sense? So, does that look like the equation phi equals pi over 4? Yeah, right? It's a cone, your angle, your vertical angle goes from 0 until that pi over 4. Does that make sense? Let me give you one other hint, or one other way you could have done this. I don't know that it's any better, but we know x squared plus y squared plus z squared is rho squared, right? We don't have a z squared, but if we just add that to this side, what do we get on the other side? 0. Not 0, we added it. So we get 2 of those z squareds, right? Right, just add z squared on both sides, and we get to there. And so we have 2, now we can replace this with that rho squared, cosine squared of phi equals rho squared, cancel the rho squareds, and now you have cosine of phi is 1 over the square root of 2. There's your pi over 4. I like that better, but I don't know if it makes much of a difference. Okay. But this idea that, right, that when you have a cone, right, you just need to figure out what that angle is, and once you have that angle, then you're in good shape. You can compute your, or you can write out your region nicely. Let's do this. This looks, I wonder if this is straight out of the book. It's a good one anyway. Let's do this. Consider, well, let me just write this down first. So, here's 2 surfaces, or equations of surfaces. Let's, in rectangular coordinates, I want us to do 2 things. I want us to draw the region, actually 3 things. Draw the region, and then I want us to describe the region in polar coordinates in sort of this form, where we say, here's what x, y, and z do, right? And then I also want to describe it in spherical coordinates, and so we'll see this region would be really nice to describe in spherical coordinates, kind of a pain in polar. Maybe we'll do cylindrical as well, as long as we have everything up here. All right. So we'll just do all 3 descriptions. So we just talked about what z equals the square root of x squared plus y squared is, right? It's that cone. And so then think about what cone opening up, sphere above it, think about what that should look like and try to sketch it. And we'll go from there. So, if you didn't get there yet, hopefully you're getting there. And again, I don't care about some perfect graph here, but you have this cone, right? It opens up, and then you have a sphere, and so you got a cone with a piece of the sphere sitting on the top of it like that. Does that make sense? Kind of a slushy, or what a snow cone shape. I'd say an ice cream cone, but maybe a waffle cone with a really shallow amount of ice cream in it, something like that. But hopefully you get the idea, right? You got this cone, and then you got this ball on top of it. And so let's start trying to describe this. So we'll start with rectangular coordinates. So what's this bottom one? That's z equals the square root of x squared plus y squared, right? And then the top is
V equals 2 square root of 2 minus x squared minus y squared.
yeah, just solve that, right? The top half of the sphere is given by that, the bottom half is that. So when we do this, and I'm going to put I guess I'll put the z's first. It doesn't really make a difference. So where did the z's range from then? From the square root of x squared plus y squared, right? The cone until you hit the sphere. And so you get the same bounds there, or those bounds here. And if we're converting, so we'll just kind of do these all at once. If we're converting over to cylindrical, z is the same thing, almost. So what would the bounds for z be in cylindrical? So we don't have x and y anymore, but what's x squared plus y squared in cylindrical?
R squared.
R squared, so you get the square root of r squared, r square root of 2 minus r squared. Does that make sense? So there's nice bounds. We haven't introduced any of this other stuff yet, so we'll hold off on the spherical for a minute. Okay, now right, so if we're doing our integral before, we take this and then we collapse down into the xy plane, right? So now we need to figure out where these guys intersect. So how do you find the point of intersection? I'll do that down below here. Well, this equation is what? Z squared equals x squared plus y squared. This equation is z squared equals 2 minus x squared minus y squared. Does that make sense? So if you set those equal to each other, now the z squared, what do you end up with?
X squared plus y squared equals 1.
Yeah, right, all right. So you end up with x squared plus y squared equals 2 minus x squared minus y squared. So move the x squared and y squared over, you get 2 of each of them, and then divide by 2. And so you end up with x squared plus y squared equals 1. And so this point where they intersect is 1, and you just have this circle down below, right? So you got a circle of radius 1 is that point of, or is that region of intersection. So let me pull this off to the side. What's the equation for a circle of radius 1? Y equals, well, x squared plus y squared equals 1, right? It's that equation right there. And so our top half is what? Y equals, well, you could tweak it, but y equals plus or minus the square root of 1 minus x squared, right? And so the plus is the top and the minus is the bottom. So if I want to set bounds now for y in rectangular coordinates, what can I do? I can do from the square root of 1 minus x squared, right, the bottom half of the circle, to the top half, the positive square root of 1 minus x squared. And then what are my bounds for x? Not 0, the whole negative 1 to 1, right? Negative 1 plus 3 to the x. Okay, so for certain functions, maybe this would be perfectly fine. And I'll just point out, right, whenever we do this breakdown of the regions like this, describing, we're essentially setting bounds to do an integral, right? You'd integrate from z from here to here, y from here to here, x from here to here. You're essentially doing the same thing. So, how about this one? Well, I've dealt with the z And now how do I describe a circle in terms of r and theta?
R 0 to 1 and theta is 0 to 2 pi.
All right, that's much easier to describe than the mess we had started with before, right? Now, spherical coordinates will be even easier. So let's think about this region in terms of spherical coordinates. So what are my thetas? Well, they're going to wrap all the way around, right? Because I've done the whole distance. So my theta is going to go 0 to 2 pi to allow me to wrap all the way around. What's my angle going to go from? My phi.
0 to 2 pi, pi over 4.
Yeah, from 0 to pi over 4, right? And that's why we had to find that equation earlier. From now on, whenever you see this, it'll show up often enough, you should just know it. The spherical equation is phi equals pi over 4. So that angle goes from 0 to pi over 4. So let me just start writing these out. So we have theta ranges from 0 to 2 pi. Phi ranges from 0 to pi over 4. And then how about the rho? So again, your angle, you're somewhere in there, but your rho's are always inside of that cone, right? So the cone is just controlled by that pi over 4. And so your rho's really, for everything, range from 0 until they hit the sphere. Does that make sense? Because you're inside that cone and you think, whatever angle I go around and my rho is between 0 and, or my phi is between 0 and pi over 4, right? I stay inside that cone, and so my rays just go from 0 till they hit the sphere. What's the radius of that sphere?
2.
Not 2, square root of 2, right? And so my rho's just go from 0 until they hit the sphere, which is square root of 2. That make sense? So this, hopefully, convinces you. That's a nice, easy way to describe a region like that, right? And so if we want to integrate, it's always really easy to integrate, or often really easy to integrate if you're going just from constant bounds to constant bounds, right? And so, all right. So, hopefully that gave you a decent overview of cylindrical and spherical. We'll stop here for this section, but then we'll come back and start doing integration in those